the sample and simultaneously record a change in temperature change. And what does this do? So let me first show you the setup, and then I'll explain what this device is doing. So in TPS, you can use the kind of winding traces for temperature sensing. So you use the winding traces to generate heat because it's essentially a resistor, so you can generate heat. And it's also a temperature sensor, so you can generate heat and also measure temperature using the same RTD device. There's also another device that uses separate heaters and thermistors. So we see it uses two resistors as the heater. You apply voltage to a resistor, then it generates heat. Then next to the heaters, you have thermistor that measures temperature, right? This is thermistor we were just talking about. So what this device doing is that it's going to apply some heat by the resistors, and at the same time, the thermistor monitors temperature change. So now let me ask you this: if we place this device in water versus in air, so how would the temperature increase differ? When we compare air and water. So you place the device in water, you place the device in air. So how does the temperature increase differently?
It increase more in air.
Increase more in air. And why is that?
Because it conducts heat better than water. Water has a higher heat capacity.
That's it. Yeah, I think you are very close. So when you place the device in water, the heater generates heat. So since water has a higher heat capacity, and it also conducts heat better, it has a better thermal conductivity as well. So what that means here, the heat generated by your heaters are not going to build up locally. It's going to spread to water. So you're going to have a low temperature increase. But when it's placed in air, so because air doesn't conduct heat very well, so heat is going to build up locally. So you will see your temperature increase much more when the device is placed in air. So based on how much temperature increase when you do this TPS sensing, you can infer the thermal conductivity or thermal diffusivity of the material you place the device on. So then if you place your device on your skin, the temperature increase will be between air and water. So it will be closer to water. And depending on how hydrated your skin is, you will see different temperature increases. That tells you thermal conductivity. That tells you hydration. Yes.
Does the sensor work with the thermistor so close to the heater?
It's so close, right?
Picking up what the heater's spitting out?
So your concern is that the thermistor is too close
to the heater. So wouldn't it just be measuring the temperature of the heater?
Yeah. So this device will be placed on the skin, and heat will be mainly conducted through the skin, not through air, because air is not very conducting.
Oh, okay.
Yeah, it goes through your skin. Okay, so we want to be a little bit more quantitative. So we have an equation for TPS. So for a constant pore density Q, the temperature change delta T of a resistive sensor with a radius of R follows this equation. K delta T over QR equals a really complicated equation on the right. So K is your thermal conductivity, delta is the temperature change, Q is your pore density, R is your resistor radius. On the right, the term that matters is alpha T over R squared, where alpha is the thermal diffusivity, T is time, R squared, is the square of your resistor radius. So this is really complicated. We need to do approximation as engineers. So the first approximation is that you can consider the alpha scheme constant is typically around 0.15. It's typically around 0.15, not much change. Then you plot this equation numerically, you will see as time increases, this term on the left will approach a constant. What that tells you is that, as long as you measure long enough, you wait long enough, your term on the left is going to be a constant. So it doesn't matter what your alpha is, just wait long enough, then your term on the left should be a constant. So this is a constant. Then, since Q and R are both constants, so you will see your thermal conductivity is proportional to 1 over delta T. That's the key takeaway. A higher temperature increase means a lower thermal conductivity. That's the only message you want to take away from this slide. Okay. All right, so how can we use TPS? So this is a case where we use the TPS device to measure sunburn, So this is a hand before exposure to, the sun. And after 5, hours of sun exposure, you will see the arm becomes really red. And the redness decreases over time. And after, about like 2 weeks, the hand returns to normal. So why does the hand become red after sunburn? Why does it become red? So this is, because after sunburn, your tissue is injured. DNA, protein, tissue, cells, they are injured. So to repair the injury, your body will try to deliver more immune cells, nutrients to your skin that is burned. So to do that, you need to supply more blood to the injured area. So that happens by expansion of your blood vessels. Your blood vessels becomes larger. That's called dilation of blood vessels. So with more blood, then your skin color becomes red. Make sense? More blood, then skin is redder, more red. Okay. So how can we quantify or monitor this process? We use TPS. So on the plot at the top left, you will see when you use TPS to heat your skin, before sunburn, the temperature increases to by about 6 degrees C. But after 5 hours of sun exposure, the temperature increase is only about 4 degrees C. Why is that? Why a low temperature increase? After sunburn,
Because there's more blood, which means there's more water there.
And how does that change thermal property? More water means
Higher diffusivity.
and because based on this equation, alpha doesn't change much. What changes is the thermal conductivity. So with more blood, more water, then your thermal conductivity increases. That means your temperature change decreases, right? Based on this equation, higher thermal conductivity, lower temperature increase. So you can monitor the thermal conductivity of the skin to monitor, the recovery of sunburn. So, after sunburn, you will see the temperature increase is lowest and the thermal conductivity is highest, about 0.57. As time goes by, you will see the thermal conductivity returns to normal. That means your skin is being repaired, is recovering.